have to get selected. So if by increasing the number of spacecraft that are launched and the number of deep space opportunities that are out there, we can get even say half of those proposals actually out there and running, then we've done a good thing for the community. However, this has to be self-supporting, and this only works at scale. So we need to do hundreds of thousands or millions of spacecraft. So how on earth are we going to do that? Also, if you look at what consumers are prepared to pay, I think video game money is where we need to be. So sort of $50, $100, something like that. And if you do the maths, the cost of launch is all down to the mass of things pretty much. And if you want to hit a price point of $100, your spacecraft need to be a gram. So that's a pretty tough thing, but it's not impossible. And just like everyone said for the last 2 days, we want to work with the regulations, we want to do this properly, we don't want to annoy anyone, we want to do this properly. And so we need to make sure that this works from the scientists and the engineers and the regulators and, in fact, the consumers taking part in all this. So we thought we ought to do a proof of concept. So in 2011, we did a Kickstarter. So we went to Kickstarter and said, would you like your own spacecraft in space? If you pledge $300, we will give you your own spacecraft that will just transmit your initials. If you give us $1,000, then you can program this spacecraft yourself. So we went up there, 315 people backed the project. And in April last year, 104 of these little spacecraft were launched to just below the International Space Station. So you've got 100 milliwatts of space-grade solar cells on here, a system on chip with a UHF radio transceiver, magnetometer, accelerometer, temperature sensor, memory metal antennas. It's a spacecraft. We launched 104 of them. People, when you put up your charts for the number of spacecraft launched last year, could you add 104 on them, please? But these are spacecraft. They are as capable as some of the earlier CubeSats. And it was great, and it proved that people were interested in this. We got to space, we did it. There was enthusiasm for it in the market. It's not a huge amount of money, $75,000, but we were lucky to receive a launch from the NASA Alana program. So in actual fact, that was enough to cover the cost of doing the mission. Now, what we did learn when we do that is that most people think that space exploration should be Star Trek. So when we came to do the next version, we have to make sure that we try and make it as close to Star Trek as possible and address all the things we learned from the Kicksat. So we want to have sort of cool-looking software to work with. But the key innovation is that we needed to shed some mass. So this little spacecraft here is a massive 4 grams. I mean, that's just outrageous, isn't it? So what we did is we refactored that into using thin film technologies. So this is a model of the Scout spacecraft, and this is a 200 milligram thin film spacecraft. It basically has all the same electronics as that little Sprite that was launched to the ISS. But for example, we take the chip out of the packaging, we use a process called lapping, which is basically diamond sandpaper, and you grind 450 microns off the back of the 500 micron thick die. We bond that onto a Kapton substrate, and then we print all the passive electronics on top, so the resistors, the capacitors, and all those bits and pieces. And by doing that, we get the mass right down, so we reduce our launch costs. And we also get something very important, which is we get mass customization. These things come out of printers. They're designed to work in microgravity if necessary, but obviously for the first version, we do it on the Earth. And it means that when we print out, say, 1,000 of these that will fit in a 1U CubeSat, every single one can be different, and it doesn't cost us anything extra to do that. So if we want to have 1,000 different designs, or people want to have their own spacecraft with 1,000 different designs, it's actually possible, and we want to allow people to experiment and play around with all those ideas. And the end point of this is we designed it to work in microgravity because eventually we want to fly these spacecraft printers in space. Well, why would you do that? Well, if you say you want to do a mission to Mars, you've got 18 months or whatever it is to get to Mars in the first place, and then you start doing your experiments. If you could fly a spacecraft printer orbiting Mars, then on Earth you could design in a web browser your spacecraft, hit file print, 20-minute speed of light delay, and out it pops at the other end. So obviously we can shrink those launch cycles and launch delays and things. So again, that's not going to happen for a while, but that's where we're trying to get to, and we're also serious about it. Okay, so you can imagine, when I stand up and say this to people, you get a few objections in the audience. In actual fact, all these objections are exactly the same objections that were made to the CubeSat the first time round, and I must admit I pinched these straight from one of Geordie's presentations, so I do apologise for that. The cool thing is this time round, 10 years later, you then get a quote in Nature from the head of the NSF program saying, yes, this is a mad idea, but just like last time, you know, maybe it's going to work out. And people, because of CubeSats, are more willing to give it a go. And the other thing is that, as you've seen, CubeSats have sort of grown slowly over time from that 1U to 3U to 6U to 12U. And of course, we have exactly the same thing with the thin film devices. So we have deployables, and they start off at this sort of size, and we have methods where they can ping out about half a meter, a little bit over half a meter. Because we need the aperture and we need the surface area for the solar cells, because there's not very much sunlight if you're going to Mars or Saturn or somewhere like that. And again, all these things have been worked on. Okay, so how are you going to communicate with these things? You don't have much power. You've got 100 milliwatts. You're trying to close a link over a few 100,000 kilometers. How on earth are you going to do that? Well, you use radio telescopes. Now, if you use, say, something like the Deep Space Network or a big radio telescope, you've got the game to close the link. But again, if we're going to have 1 million spacecraft, these are huge physical lumps of metal that need to shift around. So you really want phase array systems. So it turns out that the Square Kilometre Array, which is about to be the world's largest radio telescope and being built over South Africa and Australia, is basically perfect for this. It's going to be 250,000 omnidirectional antennas, big supercomputer in the middle, and they can synthesize multiple beams pointing all over the sky to get the data down. So there's a precursor system called LOFAR, the Low Frequency Array, which is built across Europe. So it's got about 1,000 kilometer baseline, and there are these 12 international stations, one in the UK, which is the picture you see at the top there. So that's roughly 30-meter diameter phase array antenna. And at the end of last year, on the Chang'e 5 mission, which was the lunar fly around the moon and come back again, LuxSpace flew a custom radio beacon for us on the upper stage of that launch vehicle, and we actually tracked it with LOFAR, got the data down. What's more, because LOFAR has got multiple stations, you can do multilateration, so you can do the navigation. So as long as you've got 4 of these stations and you can receive the signal, you can work out to within a few meters exactly where your spacecraft are. Okay, so we can close the link. We know where our spacecraft are. Okay, I think we might actually be able to make this work. Now the problem is, or not the problems, but now we come into the challenges of the regulatory area, and this is what we're all about. So first of all, you don't know the purpose of these spacecraft at launch necessarily. If these are personal spacecraft and people potentially generating in very short timescales, even minutes, for example, how do you file for that in advance? Is it a cluster mission? If you have a cluster mission, how different can the spacecraft each be and still be part of the same mission? 3 months, I think we heard, was the fastest we can do an ITU. That's great, but can it be done in minutes? Or do we need to think about how one day it might be able to be done in minutes? And also, if you're launching, say, 1,000 spacecraft, some of which are amateur, some of which are scientific, some are commercial, do you do a single file for all of them, filing for all of them? Do you file for the individual clumps, or whatever? Again, these are problems we're not going to encounter in reality for a while, but it's not going to be that long before we have to worry about them. Numbers were great. So we had 104 on KickSat. We're doing an interplanetary proof of concept either at the end of this year or the beginning of next year. That will be about 1,000 spacecraft. Over the next 2 decades, it's going to be 1 million. Again, can the systems actually cope with those kinds of volumes? Other problems, fees. If your spacecraft costs $99, is a $10,000 filing fee per spacecraft really proportionate for that? We need to worry about that. And of course, certain jurisdictions have got problems with it's sort of similar sorts of problems with either insurance or the registration fees. And then the other thing is, at the moment, for our proof of concept mission, we have backing from participants from more than 40 countries, which I think is absolutely wonderful. But what's the nationality of these spacecraft? Do we put them under our own house, sort of act as an umbrella and sort of act as a broker for that? Or do people want their own spacecraft? We found with KickSat, people were coming to us from nations that weren't previously space nations and saying, we want to fly our own spacecraft. We know it's only this little one, but it will be our country's first spacecraft. So how do we accommodate those people? And then if you think of things like the printed spacecraft, you're going to have ownership changing over time. You know, what's the nationality of the spacecraft designed by a Canadian that's printed on an American registered spacecraft printer using, I don't know, frequencies allocated to a French company? Yeah? And all those wonderful things. Anyway, that's a very quick whistle-stop tour. When I'm not being the crazy guy up on stage, I also have an academic hat, and we run the Interplanetary CubeSat workshop. I'd like to invite you all there to Imperial College at the end of May, where we talk about the less crazy projects, but still the very serious ones. Thank you very much.
Thanks, Michael, for your challenging presentation. I have a difficulty say how. Two small comments, if I may, just to clarify how I see the issues. That the first KickSat PCBSat project was a big surprise for us, because we were a little bit curious who can license such an operation and just release 150 KickSat projects, probably in the free amateur band. This I don't understand, but okay, probably if you can explain to us. And the second, I like your project, which is very nice, but I am strongly advising you to find the administration who will file this. There is absolutely no problem mixture, because can be amateur filing, non-amateur filing, this can be done. But please don't forget the first slide which was presented by Mr. Henry yesterday, that the outer space is certainly free for exploration and use by all states, but with the conformity of international regulation. That's why if you will find the notifying administration for any of your project, we will proceed following the radio regulations. And certainly if you find the administration who is ready to send your filing to the UN registry, there is absolutely no problem where is printed, where is made. We need one notifying administration and one launching state, and I wish you a lot of success with your project. Thank you very much.
Thank you very much. Shall I address those two questions?
Sorry? Yeah, yes, certainly. Yeah.
So the first one was, the project was originally set up to be a pure amateur project. We filled in all the IARU forms. Because I'm British, I can't actually run the project myself without being licensed by the Outer Space Act. Therefore, it was given to an American university who chose to go down the FCC filing route, and then they made the final regulatory decisions, which I didn't necessarily agree with. So I did my best. At the end of the day, it's the launching body. For the second ones, absolutely, we want to do everything by the book. We want to do this properly. We want to do this collaboratively. We do, for example, we're doing outer space exploration, so you need to worry about planetary protection protocols. We do it all properly. We don't want to take any shortcuts.
Thank you. Thank you very much. Any comments? Mr. Agapo? Yeah. What about the microphone?
I have just one question. Today in my presentation, I tried to explain why do we need to improve technology in small satellites in order to make them traceable. Those products you just presented to us requires billions of dollars in order to trace in space from the point of view of spaceflight safety. And maybe I will repeat one not very pleasant comment, but the last week in Tokyo there was another workshop on SSA, Space Situational Awareness, and Lieutenant General John Raymond, Commander 14th Air Force Strategic, Air Force Space Command, he told that the last year he was very happy that KickSats were not deployed. Because if they would be deployed, as it was initially expected, then he had real troubles, because he is a person responsible for the safety of operational spacecraft. And as you know, right now the US government is providing some sort of service for spaceflight safety, not just to the US spacecraft, but to the spacecraft of all other nations. So my question is, Do you consider all these challenges